my association, my association with Dr. Kabede has been almost from the time I joined A&T, and that was in 2000. And since then, we have been collaborating with each other, exchanging students, sharing the labs. And he is such a wonderful colleague. I think he's very open for partnership, collaboration with engineering. And I think he's always, we don't feel that we are in two different departments. And we have several publications, starting with Talisha Haywood and Adero Page, and many students from his group joined mechanical engineering department, did masters and PhD and so on. So today, this is like inaugural seminar of PREM, and I'm going to talk about Cornell Partnership for Research and Education in Low Dimensional Energy Materials. And as you can see in the blue font, it says acronymed as CREAM. So collaborative research and education in energy materials. And this is the team. You can see that it consists of a large number of faculty from A&T as well as from Cornell, from different departments, chemistry, physics, applied science and technology, School of Education, and in the engineering, several departments, mechanical, computational science, and so on. And you can see all of them. And on the left, you see the team from Cornell. And the first one, this is Frank Wise, he's the director of MRSEC. And next one is, next to him is Jin Santavich, is PhD graduate of MIT and associate professor in Cornell. And also many faculty from there, all very accomplished, and research staff. And so very humbling to work with them. And you will see that already the work has begun with them. Their students have listed already. Now we keep sending the sample and so on. So I think it's a very strong partnership. I don't have to mention the names of, you can all recognize them. Genera Waterman, Dr. Kabede, Frank from the other side of the campus, and so on. So I think these are the graduate researchers working in the PREM right now. You can see Manoshi, John Bentley, he's a PhD in chemistry, applied science technology, working with Dr. Bastakoti, and and we have a new student joining in the fall 2022, and probably working with Dr. Genera Waterman. We'll be working with her. She has been a student from Howard University. I think she had some experience of working with PREM. And Jacob is working with us, and Kaushik and Abhyadan. I think all of them are there. I think they can, I had planned that they can just say hello to each of them, to the audience. But I think in order to have a smooth progress, we can, Dr. Kabede, probably the time will not allow it, right? So that we just, they are here in the audience. And I hope this, my students from material science class 261, and I know they are here. I have started the attendance. You can mark your attendance, so then you can earn your extra credit, and so on. So these are the undergraduate students working on the PREM project. Brooke Smith from mechanical, Vanessa Jones from physics, Amina Bland from also mechanical engineering. And you can see they're all high profile students. And Brooke and Vanessa, they would be heading to Cornell in the summer to work directly there on their MRSEC project. They have applied it, and probably they would be recruited. And I think they have a very strong pool of 400 students apply, and they select only 10 or 12, and these two A&T students have secured their position there. So I think it's very humbling because of our partnership with them. And I think to I give a lot of importance to undergraduate research. Graduate research is definitely very important, but to me, undergraduate research is also very important. I think, preparing the young mind from early on is important. I think I had planned that they can give a testimonial, share with you their experience, but I don't know how it will be possible. If it was a live audience, probably they could have stood and talked about themselves. Brooke, are you there?
Yes, I'm here.
Say something.
I'm here.
Say something.
Oh, about the program, I really liked it. So far, from presenting in the one women's and physical science about this work we're doing at Cornell, or the partnership with Cornell, it helped more to do the talk because now I'm actually getting to see what I was speaking about, and like everything's coming together with this research, and not only being handed papers and then having to actually do work, but having a class during the week and actually learning the specific science and then being able to apply it to the research really helps. So
thank you. Vanessa, are you there?
Yes, I'm here.
You can say something. How is it going so far?
Say something about my summer work or about working in the lab.
What you are doing at A&T right now?
Oh, at A&T right now, I'm working in the lab with Dr. Kumar in his material science lab.
Okay, Amina.
Hi, everybody. I'm Amina Bland. Like it says, I'm a sophomore mechanical engineering major, and I'm working right now in the lab, and I'm really enjoying it. We meet with Professor Kumar every Tuesday, and he kind of gives us some information that pertains to what we're doing in the lab. And then we get to go in.
Thank you, Amina. So I think what I do that as Amina mentioned, that I meet them every Tuesday for an hour on Zoom and give a lecture on thin film research, nanomaterial research, why this material. And it goes for an hour. They have first-hand information, what's going on. And then I ask them what is the progress, and they write a summary of that meeting. And so I think it is helping them develop their writing and communication skills. And I think it's very important that they have the first-hand information from me, and I share my knowledge, and I think I enjoy it and spending time with them. We have, my slide is not advancing. We have also high school students working on this project. One is Kyle Hillard from STEM Early College. Probably he is already admitted to A&T for undergraduate. And we have also a student, Arihan Singh from Early College at Guilford. Kyle, are you there? I had requested him to be here.
Yes, sir, I'm here.
Just say a word. Say hello to people.
Hello, everybody. My name is Kyle Hilliard. As he said, I'm a senior at STEM Early College. The program has been very interesting to me. I'm actually 16, so I'm pretty young. So just being in the internship is a way for me to like figure out what I actually want to do. And having Dr. Kumar as our teacher every Tuesday, it's been very interesting to me. And he's probably the best teacher I've ever had. So, you know, I like it a lot, though. It's very fun.
Thank you. Arihan, are you there? Probably not. He has a class anyway. So I think you see these are some of the visuals are very important. Students working in the lab, and this the two top pictures are Manoshi and Jacob went in the fall last year, spent a week working in the lab doing XPS and some electrochemical measurements. And here also, I think, you can see it is not to highlight myself that I work in the lab and fixing the equipment. And I think that's very important part of the training that you just don't do on research. Fixing the broken piece of the equipment and repair, very important part of teaching and training. And this Amina doing some laser ablation experiment with Abadan in the lab. So this is very, very interactive going on. I think I'm very excited right now. So coming to the research objective, now I begin the presentation per se. The objective of this PREM project is a development of novel material, transition-based oxynitride materials, and rare earth-free magnetic materials, which can be used as alternative energy generation and energy efficient refrigeration. So two sets of materials are being developed. One is oxynitride-based transition metals, and one is rare earth-free magnetic alloys. And they have two widely different applications, but both are related to energy. One is for alternative energy, and one is for making some devices which can cut down the cost of refrigeration, such as air conditioning or refrigerator and so on. And the central thing is that we are focusing our research on lower dimensional material. Lower dimensional material there means in the picture you see is the bulk material, and the bulk material can be transformed to thin film, which is called 2D. It can be transformed to one dimensional, which is nanowires and nanorods. And then it can be transformed to zero dimensional. If all the 3 dimensions are of the order of nanometer, then you call zero dimensional. So same material being transformed to different dimension brings all together very new properties and unique property. And that is the driving physics. When the size of the material is of the order of wavelength of the light that you are using for excitation and so on, it's the properties are altogether different. And here are some examples that, like you have made nanowires and they are different diameters and they have different transitions. One can emit red color, green color, and blue color just by changing the diameter of the nanowire. And so you can realize different properties. So these are the 3 things we are working. First is new materials altogether, and then making them in low dimensional form and checking their properties. So I think very exciting. And all the students, this undergraduate students and Kyle and all, they have first-hand experience, and they have written a summary: what is low dimensional material, what is thin film, what is nanowire, and so on. I think I'm super excited to interact with them. And in all humility, I tell them that undergraduate research is not less important. Of course, graduate research is the driving force, but involving and engaging them very early on, high schoolers. Kyle, means he's doing his capstone project with me. So I think, it is so exciting. So coming to the first set of material, like first part was transition metal-based oxynitrides. These are very good candidates for photo or electrocatalysis, simply electrocatalysis or photo-assisted electrocatalysis. And this electrocatalysis is right now very hot topic to break the water into hydrogen and oxygen, which can be used as a very efficient fuel. So I'm just giving one example of a material that we are engaged right now is titanium oxynitride. Titanium nitride, probably I think everybody in the audience will know what is titanium nitride. It is again, using the basic knowledge of material science that I teach. It's a rock solid structure. And with this color code, we have indicated titanium and nitrogen here in this one. And if you substitute some of the nitrogen by oxygen, you are making oxynitride. And this titanium, so one end of the compound is titanium nitride, other end is titanium oxynitride. Titanium nitride is conducting, titanium oxide is insulating. But titanium oxide has very wide band gap. And it is one of the, pioneer material for photo catalysis. But the band gap is very wide and it cannot absorb the visible light. So there is a need to reduce its band gap. So the band gap can be reduced by nitriding titanium oxide, or I can start with titanium nitride and do it partial oxidation and make an oxynitride. But you see the two processes are so different energetically. This is my starting material, titanium oxide, TiO2, and I'm trying to make this TiNO, which is rock salt. This is the partially oxidized material. It requires 570 kilocalorie of energy per mole. And if I go from my titanium nitride route, this is my titanium nitride, and I'm reaching this oxynitride, and you can see there are some yellow ones are the oxygen. And this is the compound that you are obtaining, either coming from left side or from the right side. But it is significantly lower, 400 kilocalorie per mole energy need. So this makes a lot of difference. Not only the difference in the energetics of the two route, but titanium nitride is rock salt. Titanium oxynitride is rock salt. So it is isostructural phase transformation. If you go from the left titanium oxide route, this is a rutile structure and it goes to rock salt. So it is not isostructural phase. So sometimes there's a limit that you can put limited amount of nitrogen in that. So that is so versatile. And I have purposely put this compound formula, titanium oxynitride. Titanium is trivalent, nitrogen is trivalent, oxygen is bivalent. When you are substituting some trivalent by bivalent, hell of a work. To maintain charge neutrality, some cation vacancy has to take place. And I challenge my students that find a formula in the website or open it literature. Is there a per se formula for this compound? They have been writing titanium, nitrogen X, oxygen Y. But if I'm substituting nitrogen by oxygen, it has to be related to each other. So I cannot write independently nitrogen X and oxygen Y. And when these substitutions are interrelated, something is happening on titanium nitride and they could not come out. That is, general formula has been proposed. This is a very like a simple sit with pen and paper and try to maintain the charge neutrality and all those things. And luckily we had done a lot of XPS, and this formula, this empirical formula is tested with the XPS result. So it was very humbling. This has not been published yet. So I'm trying to gather more information, try to do these things. So this is very exciting material. This is one example, but this titanium is a transition metal. This titanium can be used by other transition metals, like a whole series can be made, but just one example is fascinating. Here I list some unique properties that you get from titanium nitride after partial oxidation. So you can see that, this is a resistivity versus temperature. Dr. Kaveri would just love to see this graph, the physics people. So this is normalized to 300K. So everything, the value is 1. Because the change in the resistance is so high that we cannot put the absolute value. So we have normalized with respect to their 300K resistivity. So you can see definitely qualitatively that some of the films are metallic. Means if the resistance keep going down as a function of temperature as you're going down, that's typical of metal behavior. But you can see that this is 45, this is 45 nanometer, this is 26, blue is 15, and after around 15, there is upward rise in the resistivity. Metal is transforming to semiconductor. It's a very humbling to see that the metal, you have transformed the metal just by changing the dimension. So this is dimensionality effect on the film. And if I teach a course on nano, so I think if my 432 nano class students are there, they will be able to correlate how the band gap of a material can be changed by changing the cluster size, because this separation of this delta E is a function of number of atoms in the cluster. And as you make the film smaller and smaller, they are reaching almost cluster kind of behavior, and the band gap is increasing. And that's what you see here. And experimentally, we have verified that. So this is a very nice piece of experiment. Now, as I told you that we are trying to develop this material for splitting of water into hydrogen and oxygen. So this is some result on titanium nitride film made in different oxygen pressure. So you can see this overpotential. People are trying to reduce the overpotential because overpotential is close to 1.5 volt theoretical, and it always comes more than there is always electrical double layer formation between the solution and your electrode. So people are trying to reduce this one by developing more conducting material and so on. So titanium nitride has shown one of the best results. I think we have the over potential is close to 215 millivolt, which is one of the lowest value reported for this material. So this is exciting result. This is for nanowire. This is not even published, and I think I'm putting in good faith here this result. Of course, it was used in the dissertation of Panupang Jepan, one of my graduate students who graduated last year. He did work on titanium nitride nanowire and titanium nitride film. So you can see the blue is for nanowire. The blue curve is for nanowire and red curve is for the. So by measuring the area of the curve, you can measure its capacitance value. So you can significant, just looking at this graph, when he brought this, I told this is amazing. And I was writing a proposal to NSF this Prem. He didn't have this, he had this data, but he didn't tell me. He didn't share. I told if I had put this data, you know, it was a slam dunk a win. This is such a strong proof that material transformed from two-dimensional to one-dimensional results in the very high realization of high supercapacitor value. So this, you can see this blue curve has significantly larger area under this curve, which is reflective of high capacitor value of the material. So this is very exciting. We are working on it, proving more and more concepts. Now coming to the second part of my research, which is on the magnetocaloric effect. So these are the two conventional way of cooling something. One is conventional refrigeration, which you see on the left side, and the one on the right side you see is using alternative technology that uses magnetic refrigeration or uses magnetic material. So here the objective is to develop rare earth free, low cost alternative material system for magnetic refrigeration. And it can be also using magnetic sensors and so on. This is bonus. But the main goal is to provide this cooling effect, develop a material. So this is the conventional way of cooling a material. You have expansion and contraction, and repeating the cycle alternatively, you realize that you obtain the cooling effect. Here in the magnetic material, but this one is gas-based, which has its own disadvantages. The gas can leak, and it can be hazardous, and the efficiency is low, and so on. So developing this magnetic material, which can be used for this purpose, this alternative technology is arising. Here there are 4 steps that is used. I'm trying to remove my cursor. In step 1, you see here, you magnetize the material, and probably the following slide will have more information. So you magnetize the material and thereby increase its temperature. So when you magnetize the material, it's it aligns with respect to the magnetic spins are aligned with respect to field. And when it happens, that time the crystal entropy increases, so temperature rises. And that time, using some heat transfer liquid, even as simple as water, can be used to extract the heat. And then you demagnetize adiabatically, and then you decrease the temperature. So adiabatically magnetizing and demagnetizing the material, you can realize a cooling effect, or it can act as a heat source or heat sink, and it can give you a good candidate to develop a technology which can be used for refrigeration. So this is shown here in more detail. Like, this is the material that you started with, and it is demagnetized, unmagnetized, no magnetic field. So it has some temperature. This is showing the mercury in the thermometer. So this has at some temperature. When you adiabatically magnetize it, now you see that all the spins are aligned with respect to the magnetic field. You can clearly see. When the magnetic spins are aligned with respect to magnetic field, the magnetic entropy goes down. because it is ordered state. At that time, crystal entropy increases and they are dominating. So by changing the magnetic entropy, crystal entropy you can monitor it. And when the crystal entropy increases, the temperature has risen. So you can see with respect to this thermometer, the temperature has gone up. And this is adiabatic. You are not allowing heat to come out and all, the heat is trapped. So now if you do, so temperature has gone up. Now you bring some heat transfer liquid and you can take that heat, and that heat is taken isomagnetic enthalpy transfer. Means that spins have remained same, but you are using some very cheap heat transfer fluid as simple as water. You are extracting the heat and the temperature of the system has gone down. Now you demagnetize the system. So here when I magnetized it, as I told you that this crystal entropy increased, that's why the temperature increased. Now I'm demagnetizing the system adiabatically. So magnetic entropy has increased. To compensate that crystal entropy decreases, as a result the temperature goes down. Now again I bring my this heat transfer fluid and realize a cooling or heating effect. So using this 4 steps, which is used very similar to the gas-based compression and expansion, you can realize this effect. So one of the main parameters that determines what kind of material, so this is adiabatic magnetization and this is adiabatic demagnetization. So the temperature difference between the two states, that determines what material you have to have this maximum delta T. Delta T is difference between this state and this state. That the material that has more and more delta T will be better candidate for magnetic refrigeration. And that's what we are trying to do in the research right now. So these are some of the material requirements. As I told you, the magnetic materials with a magnetic phase transition, it should have a phase transition, because at the transition temperature, the effect is maximum. It should be corrosion resistance. It should have large magnetization with respect to temperature, large electrical resistance to avoid eddy current. So it should not be very conducting, but at the same time, good enough conductor. And these are some of the common materials. Rare earth materials based alloy system shows promising due to magnetic and crystallographic first order transition. So the rare earth based material. So the problem is unavailability and expensive. Not only that, my students brought to my notice the rare earth materials like gadolinium and other things. They are not really rare. They are available, but their separation from the rest of the elements is very expensive. And on top of that, it is available only in the abundance wise is as abundant as copper. But separation of copper from the mineral is much easy than separating these rare earth metals from the other thing. And they're almost same in the size. So you cannot separate hafnium, gadolinium, ruthenium from each other. And it's a problem. So rare earth comes from many, not per se because of the rarity, but the cost wise also. And on top of that, it is, as you can see in the graph, most of it is available in China. So I think a lot of dependence on one country. So I think there is a need to develop material which can meet those requirements which I laid out in the previous 2 graphs, magnetocaloric material. And rare earth material, they are used because they have high moment. So the change in magnetization is much more drastic in this magnetocaloric effect scales with the moment. And this rare earth metals have higher moments. That's why typically they are used. So this is again just capping this. This shape memory alloys are used. They show the effect around 6 Tesla and 350 Kelvin. These are some of the composites. It is at 1 Tesla but low temperature. Perovskites, lanthanum, calcium, manganese oxide. They low field at around 230 K. So these are good candidates. They are very close to room temperature, and field is also not very high. So this, they have shown some promises. And people also shown Fe cobalt and nickel manganese alloys around at 1 Tesla and at 350 Kelvin. And there is some report of Fe cobalt scandium system at this one. We are developing altogether using some kind of common material, just iron, which you all know. And in that iron, by doping with tantalum, which is 5D element. So there is a good hybridization of iron 3D and tantalum orbitals, and that can give a strong coupling, and that material has shown some or good promises for magnetocaloric effect. So this is the typical melting temperature of iron and tantalum is very high, rare earth free alloy. So this is definitely not any rare earth element involved here. Improvement in corrosion, this is corrosion resistive, promotion in the magnetic phase transformation, and both Fe3D and tantalum are D block elements. And you can, looking at this graph, people a little bit familiarity with the phase diagram, they can immediately remember iron phase diagram. And still, you know that it is their mechanical properties are improved by doping very little bit of carbon, and very similar phase diagram. And this also is very hard material, mechanically corrosion resistance, and on top of that, we have shown that it shows a magnetocaloric effect. So that is the bonus. So we use our research is based on the, as I said, the low dimensional material, not on bulk. So first low dimensional material is thin film, is 2-dimensional. So we make using pulse laser deposition method. In pulse laser deposition method, you have a laser source and you have a target. So your target would be iron, tantalum, or when you are doing titanium oxynitride, you put titanium target there, and you bring the laser, and basically laser interacts with the solid material, laser solid interaction. It increases the surface temperature very high, materials comes as a vapor, and you deposit on the substrate in the form of film. And this, I'm very proud of this image to share with you. This was developed several years back, almost 10 years back, by one of the undergraduate students working on the project. That time we had a NERD project, which was also funded by NSF. So he developed this one and using SolidWorks, and I'm still using it. Many conferences, many places I have used, and it gives such a strong visual of the ablation process that I continue using it. And I have been telling my current group of undergraduate students and high schoolers that please develop something, and that will remain with me forever. And Kyle is very good with SolidWorks. So he's trying to develop something. And I think in his capstone project, he will show me something, and I will use that, probably replace this one with some image or view developed by him. So these are some typical parameters. Of course, you have to do in high vacuum. You keep some target substrate distance, use laser energy in this range, and so on. It's a typical, this is the structure of the material. So this is the iron tantalum phase diagram, unit cell. Just looking at this one, you can tell, if you apply your material science knowledge course, how many atoms of iron, how many atoms of tantalum per unit cell. Iron is 8, and tantalum all are inside, so there are 4. And this, so 8 divided by 4, that is 2. So that's why the formula is Fe2Ta. And this is the this number of atoms can be used in actually finding the Bohr magneton, and so you can find whether you get the theoretical value and all and so on. So this is important information, and I always keep telling my students that material science class that I teach at the sophomore level is very important, and I think the science never change. Even the physics that you learn in the 12th grade or in your junior year, senior year, it doesn't change. And I keep advising that open your physics book, open your chemistry book, and freshen your knowledge. Nothing has changed. This you have learned about many atomic structure, bonding, Hund's rule, and this Pauli exclusion principle. Those are the things that you use to find the magnetization, how many electrons are paired, unpaired, and so on. So I think research is building on the foundation and fundamentals. And fundamentals, your knowledge of physics, chemistry, engineering, always handy. There is no great research, even if you are doing MIT, Harvard, anywhere, unless you have your basics and fundamentals are clear, you will not be able to make a cut. Then after we check the phase purity using X-ray diffraction. You can see there are not too many peaks, so the films are almost textured. Then you use some of the standard characterization to see the roughness, atomic force microscopy, transmission electron microscopy, and all those things we do and share with my students how AFM works, how TEM works. I think it is more important for me to teach and tell them how it works, and then of course interpret the results. So you can see this is the substrate, this is the film. Film is almost single crystal films of iron tantalum. And this is the equipment that Dr. Kabede was mentioning, that we have. This equipment physical property measurement system is almost now 15 years old. And to be honest with you, I think it has more downtime than its functional time. And I think it's high time that we write another proposal to MRI or NSF and acquire a system. And it is a very powerful technique. It can do transport, it can do magnetic, it can do Hall effect. You can measure the charge carrier density using this configuration. You can measure R versus temperature in field, zero field, and using this VSM features, you can also measure its magnetization, DC magnetization, and so on. So it's very powerful, and it is working from last 10-15 years with some downtime. And I've been lucky that we get some support. And it is fully accessible. It is not that Dr. Kabede was giving a testimonial to me. I think all the facility, PLD or XRD or PPMS, all those things are available to everybody. And the people, students from physics, chemistry, they come and work. And I have publication with Dr. Basta Koti from chemistry, with Dr. Kabede, many papers. Together, I've started a partnership with Frank from AST. So I think it's open, available to everybody. So now showing some of the results. This is the basic magnetization versus temperature measurements. You can see that all the curves has a peak with respect to a moment on the magnetization on the y-axis, and that peak is a function of the field that you apply. So you have the highest peak when the field applied is 0.25 Tesla. And using this this M versus T graphs, and this is called indirect method of measuring entropy. Normally people measure entropy directly. This is the indirect way of doing, using this Maxwell relationship. And you differentiate this magnetization as a function of temperature over the entire field. And then you get this graph, and then we do a simple integration, and that will give you the value of change in entropy here, which is, I think, did I miss it? In this graph, I will come back to that one. So this is Maxwell relationship. You rearrange it, integrate it from two fields, and this gives you delta S. So basically you are measuring the dm over dt and integrating over the entire field, and you get delta S. And once you know delta S, change in entropy, then you can find the refrigeration capacity. So this is the graph, this delta S plotted as a function of temperature at many fields. And this value is close to 6 joule per kilometer per meter cube. And this value is not as good as people obtain for gadolinium, but that field that you get this value is very low. So that is the one point which is very promising. And I will share with you in a moment. This result was very good. We published in AIP Advances, and it got editor's pick. So out of many articles, 4 or 5% of the editor articles are picked up by the editor, and then it was put as a news report also. So this is very, the other interesting thing is that there is a crossover temperature. The same material gives the positive entropy change and negative entropy change. So this is the coexistence of positive and negative entropy. So same material can be used depending on the temperature is as a heat source or heat sink. So this is a very good indication of quality of the material. How do we get it? So this, as I had told you in the beginning, I think the material to show magnetocaloric effect, it has to have phase transition from one phase to other. And that phase could be sometime even the structural phase transition. Here it is magnetic phase transition. It is transitioning from paramagnetic to antiferromagnetic to ferromagnetic state. So how it happens, you can see, this is the game that is played by tantalum. This is the iron 3d6. This is standard Pauli exclusion principle. You do this, you start pairing the electrons only once the first orbitals are, first boxes are filled singly. So this is tantalum, which is 6,2, and this is 2 electrons. This 2 electron can align with this one. It can couple the 2 iron atoms like Fe2Ta, as I told you the structure, which also came from the X-ray and the unit cell. This is quenching the moment of the 2 iron atoms. This electron is coupling with this one. So now the 2 iron atoms are coupled antiferromagnetically with each other. You can see this spin is up. So this, when I force, when I little bit pay attention, this is the spin down of tantalum. This coupled with iron spin, and all the spins are parallel here. And this spin is up of tantalum. So this with the coupling of the spin will take place with iron which has spin down. So you pay here attention, all the spins are, in this one is all 3 of them are up, all 3 of them are down. So this has given birth to antiferromagnetism. Earlier it was ferromagnetic at some temperature, and when with the help of tantalum, you got this one. So this is one set of mechanism. Tantalum is also known for oxidizing very quickly. It is known as oxygen scavenger. So if tantalum during ablation formed tantalum oxide, this single bond, this bond can break and couple again to iron in a very similar manner if it was pure tantalum. So these 2 probable means and ways is bringing about the antiferromagnetism in the material, and at that temperature you have the maximum entropy change. So then this is some correlation. So that you saw that there is a crossover temperature from positive MCE to negative MCE. MCE is magnetocaloric effect, and this is the crossover temperature in blue curves, and this is the antiferromagnetic paramagnetic transition temperature, which you measure from the M versus T curve, and you can see there is a direct correlation, 1-to-1 correlation between the two. And using this, you can tune the material. The sign reversal in the entropy change could be associated with the magnetic phase transition from antiferromagnetic state to paramagnetic state, and that's how the magnetocaloric effect was significant. And this is another, probably this could be the last or second last graph. So this is the entropy change plotted as a function of field. And for the comparison, we have put this is the gadolinium. This is the gold standard in the area of magnetocaloric effect or magnetic refrigeration using magnetic materials. So it has significantly higher value. You can see my x-axis for our material is maximum 6, where it rises depending on the field. It is 20, 10, 15, 20, same unit. But and this is as a function of field. So you can see it has gone up to 1 Tesla and still it is rising. But in our case, you can see the saturation is at very small field. This is saturating just around 0.2 Tesla. So the mandocaloric effect that you get is at very small field. And this cost of this guy and cost of the iron tantalum, you cannot even compare. It's our material is very common material, iron and tantalum. So it is, and you have realized this effect. This is the most important part of the result. And comparing with gadolinium gives you that sense of appreciation that how it has been done. So this is a very nice result. And as I mentioned to you, this is I concluded that we have made iron tantalum in thin film form using PLD, and the mass specific entropy change are small compared to existing rare earth based materials such as gadolinium. However, the entropy change reaches maximum at rather small field, which is a big deal and important achievement in our lab. And as I had mentioned to you, this is this article was published in AIP Advances and selected by the editor as one of the most read articles, or his favorite or her favorite. We don't know who the editor was. And then it was recommended for a news release, which was done in AP Scilite. And this is the view graph from there, which is the schematic of those steps. This is our graph. This is the mechanism. And these are some of the publications coming from this material and so on. And with that, I end my talk. We have a few minutes for question answer. So thank you everyone. Dr. Kaveri, thank you for giving me this opportunity. I hope my students from my material science class and nano class, they have marked their attendance, and I'm ready for questions. Thank you.
Thank you very much, Dr. Kumar, and thank you for the audience for coming. Today, for the first time, probably we have the largest audience in a physics seminar. Definitely the research in the program that you're running, Dr. Kumar, is very important, and there are a lot of followers and students. And one announcement, there is I believe this is designed for students, postdocs, and I think for all audiences. There is a survey or some sort of a feedback questionnaire. Please fill out that questionnaire. I believe this is part of the program. So please do that. I appreciate that. And then I'm opening the floor for questions. Do you have any questions?
One question. Did you do XRD on the first samples you're showing? And how much oxygen did it say you had?
For oxynitride, is that right?
Yes.
Who is the question coming from?
Me, Floyd James.
Floyd James. Yeah, definitely it was done. I mean, I can put the in terms of how much oxygen means you want empirical formula, is that right?
No, the question was you were debating whether you had X and 1 minus X. And your students were saying you had 1 minus X and Y. So the question is, could XRD solve that problem? Could it tell you how much oxygen?
XRD, not only XRD, but we did more precisely using XPS at oxygen, and we exactly, I mean, I'm looking for some theoretical work on that so that we publish that with evidence, definitely. And 5 millitorr, 10 millitorr, 50 millitorr, 25 millitorr, they gave different composition, and as a result, different titanium defected titanium site to maintain the charge neutrality. So everything comes in one direction, Dr. Floyd James.
Okay. But you're saying it is X and 1 minus X, not X, 1 minus X and Y. It is X and 1 minus X.
Yeah, I don't know why when you are doping nitrogen with oxygen, you cannot call nitrogen N, oxygen Y. or vice versa. You have to, if you are putting X, then nitrogen will become 1 minus X.
But that was my question. What did XRD say you really did? I know the theory, but what did XRC say happened?
Of course, yeah. I'm not telling exactly. I confirmed with the XPS,
right,
which is much more precise way of doing it.
So XPS says it really is X and 1 minus X. Okay.
Yes, sir.
Okay.
I have one question.
Dr. Korede, before I answer your question, I want you to attend the next 2 meetings, because I want to announce to this audience, there was last week PREM conference, and Dr. Kabede was all over the place. His question was liked by the NSF program officers, audience. He brought so many strong and important points, and we had not talked to each other. He independently brought those points. It was very appreciated. So I want Dr. Kabede to definitely come to that NSF meeting, which is on 24th of February for all PREM PIs. And I think you can fearlessly raise some questions, and it will be appreciated. Yes, Dr. Kabede, go ahead with your questions.
Yeah, in I believe the last slide where you showed the crossover temperature,
yes,
as a function of, I believe, field, or the you were plotting the antiferromagnetic transition versus field or something like that. The two correlate each other, definitely. Yes. I was hoping that there is some sort of a scale factor, it looks like.
Yeah, you can see the separation is decreasing as the field is decreasing, and then finally they will coincide, of course, at zero field. Yeah,
like maybe the value for the graph. Let me remove this one. For the to paramagnetic transition temperature, yes, and then the crossover temperature, it looks like there is some scale factor. There is a scale factor. Wonderful. Yeah. So that's why you are my collaborator. So we can propose some equation to. Yeah. It's very interesting. Okay. Dr. Tang, this looks like thermodynamics or something like that is in the game here. Do you have any questions or comments, please?
That's what I'm about to do.
Yes.
Yes.
So go ahead. For a typical refrigerator, there are 2 parameters describe the performance. One is the coefficient performance. The other is, so say if you set the whole thing in a adiabatic setup, you just run your cycle, then how many and what's the temperature change of the system? And I wonder what you can say about the system you have now. That's my first question. Even 1 Kelvin, if this adiabatic magnetization and demagnetization, if the temperature change even is just 1 degree between the 2 states, it can save the energy by 30%. The calculation have shown. So I don't know what question is how much is the difference in the temperature between our adiabatic state and the, so our value is just 1/3 less than the gadolinium. So we are pretty close to the material in the market. I guess related to this, even gadolinium is not commercially very successful yet, right? I will not dispute on that. You could be right. Yeah, okay. Of course, the magnetic refrigeration is being talked about, but is it in the market and all? And how close we are? Yeah, that's fine. Clearly, more work we need to do. Yeah. So, I guess to your initial point of low dimensional. So how do you see the dimensionality play a role here? Because most of the phase transition, we are not particularly talking about those, right? I think you are so right. Do you want me to give you all the results in one colloquium? No. I'm just curious. We have done, I think, my student Kaushik has done iron nanodots in titanium nitride matrix, and he has got fantastic result. that is dot is 0 dimensional. And he is stationed in University of Nebraska, Lincoln for 2 weeks, confirming the result and calculation. And our manuscript is submitted to physical review materials. We are waiting for the review to come out. So I think we have done it. But you are right that we just showed it for film. And film per se is 2-dimensional not, but I think, there is effect shown for 0-dimensional material, where the transition is just because of, is not antiferromagnetic, ferromagnetic. Transition is from blocked state to non-blocked state, from superparamagnetic state to that. So that is coming there, sir. You are so busy in your undergraduate lab that you nice to see you.
Thank you.
One of the important aspect of this meeting is that we are, Dr. Kumar and his group and myself are positioned to really make a difference in the PREM world. And we have at least now one student, Vanessa Jones from physics, joining. I hope that more students will join activities and programs like this on campus, and then eventually, make their way into big summer research programs elsewhere. So that's what, the PREM is going to be one of the bridges. As Dr. Kumar mentioned, there are several PREMs around the country. We have access to all the resources and the human resources, including colloquium speakers, by the way, for our future. So think like that, look at it wider. And one reminder that I like to make is that this is the largest gathering in the history of physics department. I don't remember so many people coming to a colloquium. If you don't mind, guys, turn on your videos, and I like to take a picture. We will send this to NSF. So we have so many audience. Okay, please turn that on. And we continue taking questions, please. By the way, Professor Ashot Gasparian, our department chair, is with us. He's watching.
And also, Dr. Kabade mentioned research, but I think taking courses also, like, hello, nice to see you. Taking courses, like I was asking Vanessa, could she take the nano class that I'm teaching, or other seniors could take that class, or even my students or engineering students taking senior level physics class, not only physics 1 and physics 2, but quantum mechanics and all those courses. And I think that is also his partnership. So I think learning from each other, it's a very important. I think me and Dr. Kavede, I think probably with no bragging more, I think people have sensed that we have worked for a very long time. I think my collaboration is the oldest with him. And I think there is no hang up between us. That is the best part, that he just comes and I want to do this. And if I do that. I tell him that, I need some help on this one. I need some student. And he is amazing. I think this is called partnership.
Nice. I like to acknowledge Professor Kizito. He is, I think we had in our first PREM meeting, we were together. If you have any comments on student training and things like that.
Oh, thank you so much for the opportunity. I'm glad to invite your students who have finished masters to think about taking a PhD in mechanical engineering, and we are ready to take you and others who would like to do a master's in mechanical engineering. We are ready to collaborate with you all. And again, given the new technology that you see over here, it would be great for you to increase the technology readiness level from something that is just found in the lab to something that is found in Walmart or wherever your favorite store is. So again, we need to make that transition, but it happens when you come in and take a PhD. Thank you so much.
Thank you very much. Okay, more comments, please. Students.
Students, my request is that please mark your attendance and do that survey. It will be used to share with NSF and to improve our program. So kindly take a moment to do that. That is the help. And I think Dr. Kabete, if your request was not met overwhelmingly, because people have not switched on their camera, and I don't know whether you have taken the pictures.
I have taken a few snapshots, you know, if some of them don't want to show their face, no problem, we can
Sure,
see.
sure, 100, I fully agree with you.
Okay, I'm taking pictures, thank you. Yeah. Okay, thank you very much. Okay, Professor Gasparian?
Yes, I'm here. Can
Yeah.
you hear me?
Yeah, we can hear you.
We can hear you and we can
Yeah,
see
it
you.
was a nice seminar, by the way. I enjoyed that. I have a more question related as administrative. Can we actually use your courses for our students? Because, for example, this semester we tried to arrange solid state physics class, and it didn't work out much. And actually, Kebede knows more details about that. Could we actually instead send our student, whoever is interested in solid state concentration or not concentration as that direction, to share with your classes at engineering, right? Is that possible?
It is, why should it not be possible? It is 100% possible. And I think Dr. Kizeto, who is a graduate program coordinator, he can shed more light. I believe in working together. I means even if you cross list your course in your physics name, so that no, sometimes the prefix can, in the name of prefix, they don't want to take. But mean 432, for example, nano class, you cross list with your course. So the student get that it was a physics course and they will be served. So a student credit hours and so on. So I'm very open, and not only that, we are trying to develop some course in partnership with Cornell, so the quality of the course could be even better. So why not? I don't see any reason. And my department chair is also very supportive. He is 100% behind me. So I think if we bring this kind of proposal, he will be happy to handle it.
Yeah, at the graduate level, we allow our students to take courses with physics prefixes. And in fact, at the PhD level, they can take 2 of them. And then at the undergraduate level, we have what we call a science elective. Students can take any physics class as part of their curriculum. So already that's happening. And I've also seen some physics students in taking fluid mechanics and aerodynamics.
Yeah, and also I believe Vanessa Jones is taking the nano class. Am I right?
She had some time conflict. She could not come.
Right.
I wish she was.
I think the problem with you know, physics 467 is the same thing. The students are oversubscribed, so to speak, to different courses. That's the reason. But with Prem coming in full force, probably we turn on, you know, we may get some support here and there and have some students be in courses. So, but in any event, it can be done.
Let's work on that, yeah.
Yeah,
That will release our manpower.
Dr. Gasparian, we are trying to develop, we are trying to start a material sciences specialization, concentration. There we can list some of the physics course also, so that they can get a specialization in the undergraduate level as well as graduate. Yeah. That just increases their market value, that they have. So I think we can come together and work our department is very open. I can tell one of the most open departments in in the engineering to work with you, and even chemistry.
Okay, any comments, any additional comments, questions? Do not forget February the 24th, am I right? The PREM meeting. If people want to listen, we will inform them.
Yes,
100%. Yes, that will be very good. And I hope that the mission, Vanessa's mission, with her friends at Cornell, will lead to a big research result, and she will have a good time there, and more students will join us in the coming summers and things like that. So if there are, Vanessa, do you want to say something? We are sending you, you are our, advanced team, so to speak. Open Cornell University for our department. You are going to be in front, okay? You are the front line. So thank you for agreeing to work. And I believe the letter of recommendation thing will be worked out. I have been very busy working on exams and things like that. And Professor Kumar?
Okay, sir, yes.
Yeah, go ahead.
I'm thankful to you for giving me this opportunity, and what else? I'm so delighted to work with Vanessa, and I think we share the vibes. I think I can my Monday Tuesday lecture or interaction with undergraduate students are recorded, and I can share the report how they write, and I correct it, send them back. So this training is, I didn't want to tell in the PREM meeting that how we are training our students. We go all out to help and work with the students.
Very nice. I appreciate Professor Kumar and Professor Kizito. And then I think we can end the seminar here, and then we will see each other again in the next seminar. Thank you very much for coming. I appreciate it.
Thank you so much. Take care, Dr. Kabede.